now we are moving to Germany, where we should see our good friend Nicolai Moos from Ruhr-Universität Bochum. Nico, can you hear me? How are you?
I'm fine, thanks. Nice to see you.
Perfect, perfect. Great to see you again after, I don't know, several months. Yeah, good, good.
Yeah, it's been a long time.
I hope and I think you're ready because you're an excellent speaker and I think you will, you know,
yes,
surprise us with something.
Ready.
Yeah.
We can start.
So, yeah, floor's yours. So you can introduce yourself if you wish and you can start. Thank you.
Yeah. Thank you. Thank you for the introduction. Yeah, as Viet already told you, my name is Nicolai Moos. I work and live in Bochum, and in terms of the whole Spatial project that builds the frame of this session, I will show you some short presentation of a recent study that we are on. The title of the study is Geo-Spatial Analysis of Population Density and Annual Income to Identify Large-Scale Socio-Demographic Disparities. Not that handy, but yeah, we have not so much time, so I will try to rush a little through it. At first, a short introduction. So what exactly are socio-demographic data sets? Firstly, they provide information about the population in a certain area. That can mean you have measures for age, for family structures, gender distribution, household size, educational level, etc., etc., etc. So you can see there's a huge bunch of information about the people in the room, in space. And as a consequence, these data sets are a crucial mean to measure, firstly, proportionalities. Then they are also a crucial mean to detect areas of disparities. And last but not least, they are also a crucial mean in terms of geomarketing, which we will obviously hear something more later. Political decision-making, target group advertising, site searches, urban planning, etc., etc. So this is what socio-demographic data sets are about concerning the content. The structure and scale. So socio-demographic data sets usually come in table form. This is a very nice and neat format, but still this gives us no option to work spatially on the data set. So what we are looking here for now is we want to have socio-demographic data sets that are linked to geodata or stored inside geodata. When dealing with socio-demographic data sets in spatial data, we have several types of spatial details, several types of feature sets, let's say. Yeah. So the biggest thing you can measure about is the country. Then we go over to the states, to the administrative region, to counties, municipalities, districts. And the last one, or mostly the last one that is dealt with in recent studies is the statistical borough. So this is the, let's say, most of the time high spatial detail that we can obtain socio-demographic data sets. The question is that all, or can we get more? Because the statistical borough is a nice feature, a nice unit, but still, if we want to go into further detail, we need to have smaller units. So what's the point? Usually, socio-demographic data sets are distributed in postcode polygons or other area-wide and gapless data sets. I will come to that later and show you what that means. These are also, they're quite small, but they are not as small and as specific as we want them. I will come to that now. So what are postcode polygons, or in this case, in this case study that we are dealing with in North Rhine-Westphalia, Germany, what is PRZ8? So PRZ8 is a feature that is has been commercially created. It has the approach that approximately 500 households are fitting into one feature. You can see in the graph below here that there is the scattering goes from 12 persons per feature to more than 1,000 people per feature, households per feature. That leaves us with the problem that if we want to take 2 or more features and compare them with one another, it might be the fact that we compare 12 people to 1,000, and this is not very handy. So Still, you can make maps out of these data sets, maps that deal with larger areas, like here, North Rhine-Westphalia in Germany. I just put two attributes, two variables in scale, so you can see what these data sets might look if you make a map out of them. The first one is the population density, so the number of inhabitants per square kilometer. You can see very clearly that we have north of the Ruhr, we have the Ruhr area with Dortmund as the biggest city, and along the Rhine, we have the Rhineland with Cologne as the biggest city. And these two regions make the most populated, the most dense populated part in North Rhine-Westphalia. The second attribute is the average annual income per inhabitant. In this case, we have indexed the whole thing. So that means if you have the average income, you make the value of 100. If you are richer, you have a value above 100. If you are poorer, you have a value below 100. So you can see here that there is a huge variety across North Rhine-Westphalia. This variety is concerning the macro perspective can be seen very clearly, but these are two maps. What if we say, let's make it in one map? There's a basic concept that deals with bivariate choropleth maps. That means if you have two different attributes and you make them sequential and put them into three different classes in this case, with rising intensity from bottom to top, then you can link them and put them into some sort of matrix variable like this one. That means if the saturation of the respective color gets darker, then the value gets higher. Yeah, so you can link two different attributes and put them into one map, which looks then quite like this. So now we have a decent insight into the spatial pattern of the two variables in one map. As you can see, the two zooming windows here from Cologne and Dortmund, you can directly see that Cologne has rather darker colors and Dortmund has rather lighter colors. Yeah, so might be the interpretation that Cologne is in average a little richer than Dortmund. And this is a nice interpretation, but still, it's only a rough division of bigger areas. So Cologne and Dortmund are, as I said, big cities. And the detection of large-scale patterns is here not possible. So we want smaller units. So people do not live everywhere. And how do we do this? Now we're coming to the analysis. On the left side, you see the postcode polygons, PLZ8. This is, as I said, area-wide. On the right side, we have an overlay layer that has residential city blocks. So these are the one specific areas where the people actually live. And these are the one areas that have the higher interest for us. Yeah, all the white areas on the right side, they don't mean anything to us. We want to know how are the people, where are the people, and how are they there. So we did some sort of three-class isometric mapping approach. It was let's say, rather complex, but the main information that you have to get out of this scheme is we put several additional data sets into the whole process and created a relative value, an allocation factor for each residential city block. And these allocation factors were put relatively to all the other city blocks. So we could put the main value from the bigger feature and distribute it to all the respective city blocks to take one big value and put it into the smaller ones. What we also did in the analysis was some sort of clustering. So we had the K-means algorithm, and that meant that the K-means algorithm prefers cluster with a low variance and of similar sizes. So we try to put these two variables and put them into some sort of boundaries, let's say. Yeah, and if you look at the boundaries for the PLZ8, what you can see here. In a scatter plot, you can see that there is a huge scattering. So the features, each point is one feature, and the size of the points is relative to the amount of people living there. It's very scattered, and the boundaries between these different classes are not that clear. Coming to the results, we can compare the scatter plot, the smaller one at the bottom left, with the one that we made after the disaggregation. So the one at the top right is the scatter plot of our residential blocks, actually. And you can see the scattering got way lesser, and we have clearer boundaries in between our different clusters. and also the connection between the two got a little more clearer. Let's see that in a map. What does it look like? So this also, again, is the city of Dortmund. On the left side, we see the PLZ8 polygons in their two respective variables. And now you can compare it directly to the one values we have since we have disaggregated our thing. So you can see the pattern. The pattern you can see, it's basically the same. So the colors match somehow from left to right, but still you have a much more higher level of detail. So you can really look into the one city blocks, into the one perspectives in the smaller city areas, and directly can see how are the people there living there. Another example for a visual perception is the clusters. So I took the first two clusters, number 1, number 2, which means these two clusters contain the one people who live in areas with a very high population density and live in areas where the people are rather poor. And now you can see on the left side in the zoomed window that there is no real area around this dark reddish feature. If you put it in the right side and you have the disaggregated values, you can see that the picture is much more distinct. Yeah, so the possibilities to distinguish between certain areas become improved a lot. The last one I want to show you is a local perception, let's say, because we have this bluish contoured feature is the Klarenberg in Dortmund. The Klarenberg is this kind of buildings, the structure where actually there is a very high population density and a very low income average. And the feature from the PLZ8 you can see on the left, this is some sort of, let's say, automatically generated feature, and the boundaries of the feature do not fit the boundaries of the Klarenberg. So the Klarenberg feature of the residentials, you can see on the right, fits much better into the boundary of the real Klarenberg. So and after the disaggregation, after clustering, you can see that the one feature overlaying the Klarenberg here on the left side is put into cluster, which cluster is it? Let me see. Into cluster 4, I would assume, 3 or 4. So it's not the lowest cluster. But if we disaggregate our data sets and put the new values in variables into the new features, then we get new values for this one feature and the one feature that fits the Klarenberg. And you can see that the state of the values of this one feature now fits way better to this sort of structure, because the people who live here, we know that from different studies, they have a lower income than an index of 81, and there is a higher population density than 40,000 people per square kilometer. So obviously this technique works. It has to be improved. It has to be applied to several other case studies, but it works. And might be a nice mean to improve the geo-marketing, to maybe make a short bridge for the next session. Yes, thank you so far.
Thank you so much, Nico. It was really interesting. Thank you for your presentation. And you all have seen how geography could be applied to get some more information from the data. But remember, garbage in, garbage out. So you need to work with the data very carefully, and based on that, you can do good decision making.